this video, I'll be discussing spring block system while external force is present. So, for example, I'm taking this example that there is a spring and there is a spring block system, and they suppose that we are applying some external force, constant external force, F. So now in this example they might be interested in knowing, first find out the equilibrium position, second case can be asked find out the time period of SHM, and third point can be asked find out the maximum extension in the spring. Okay, so this is highly important question because external force is also present. So what you need to do, there are some assumption. Assume massless spring, stiffness K, or spring constant is K, frictionless surface is present. So now when I am talking about equilibrium position, we need to see, suppose that if we are applying this force, let's say at this position the spring is elongated enough, let's say x equilibrium, then there will be kx equilibrium force on the block and obviously F force. If F is equal to kx equilibrium at this moment, then x equilibrium, extension at equilibrium, will be F by K. So this will be the point of equilibrium. So we got the first answer. So here equilibrium means force, net force on the block should be 0. So we are just utilizing that fact only. Now you need to understand, at this point particle will not stop. This is the just point of equilibrium. So what is happening, understand, initially when you apply certain force, the acceleration will be F by m only, because there is no extension in the spring, right? But suppose that when this x equilibrium is coming into the picture, that time force is 0, that means acceleration is 0. That means acceleration is decreasing up to the equilibrium point to 0. That means this particle will attain certain velocity at this moment, right? So at this velocity, and that velocity will be the maximum velocity. So particle will not stop here. So let's say particle stops further after traveling certain distance. So let's say particle stops here. So now at this moment total extension in the spring is, let's say, capital X. Then force will be capital X, and of course this was the F which was applied here. So let's say instantaneously particle stops. So if that is true, that means velocity will be 0, and of course we know that initial velocity when spring was not compressed, this velocity was also 0. So that means there are two different positions now we can see. So we can apply energy conservation in order to find out the maximum extension, right? So for maximum extension, we can say, let's say this is the point A and this is the point B. Energy conservation between point A and B. So if you do that, you need to write work done by external force F will go into the change in elastic potential energy, EPE, spring. Correct? And if that is true, then we can write work done by external forces. So this force is F, so this would be F dot capital X is equal to half K into capital X square minus 0. Initially it was not compressed. Now you can see F is also in this direction and X is also in this direction, theta 0. So this is Fx cos 0 half K into capital X square. This X is cancelled out. We achieved the value of X 2F by K. So we are getting interesting result that X equilibrium was X by K, F by K, and capital X is 2F by K, right? That means double of this. That means this is X equilibrium, this also X equilibrium, which is F by K only, correct? And now the last one is there for SHM. So for SHM, what I need to do, I need to displace the particle further from its mean position. Mean position means where equilibrium point is there. So let's say this was the point of equilibrium. Equilibrium position. So if this is the equilibrium position, let us displace this particle X further. So if you draw the FBD of this particle, so this is spring, we'll put Kx equilibrium plus X, because net extension will become X equilibrium plus X, and of course there is a force which is applicable, so that means there will be acceleration, right? So I can write F net is equal to K into X equilibrium plus X minus F. That means force in SHM. So that would be equal to F minus F net, and that would become F minus, so let's say write this F dash, because this is also F, so F minus K X equilibrium plus X. If you multiplied this inside, this will be Kx equilibrium minus Kx. This is F dash. Interestingly, earlier we have proved that F is equal to K into X equilibrium. So if you utilize this result, we can write, instead of Kx equilibrium minus F, this is Kx. This is cancelled out. So F dash is equal to minus Kx, right? So interestingly, this time F dash is equal to minus Kx, then time period can be written as t is equal to 2 pi under root of m by k. So the time period again k, but mean position shifted. Instead of 0, mean position is X equilibrium is equal to F by K, right? So shifted mean position but the same time period. Getting my point? So how it is doing SHM, this is the mean position, and of course it will go like this and then it will come back like this, and it is performing SHM in this region. Okay, so that's how we calculate all these parameters during SHM when external forces applicable. Got it? Yeah.